Hello, fellow explorers of the cosmos. Today we embark on a thrilling journey into the heart of light itself. Prepare to be amazed as we unravel the secrets of electromagnetic radiation and its captivating wave nature. From the vibrant colors that paint our world to the invisible signals that connect us globally, electromagnetic radiation is the language of the universe. Understanding this language unlocks a deeper appreciation for the intricate workings of our cosmos. Fasten your seatbelts and get ready for an adventure into the fascinating realm of waves. Imagine a boundless ocean of energy, invisible yet constantly surging around us. That's electromagnetic radiation. It's a form of energy that travels through space as waves. These waves are created by the movement of tiny charged particles called electrons. Think of it like this. When you throw a pebble into a pond, it creates ripples that spread outward. Similarly, when electrons vibrate, they create ripples of energy, electromagnetic waves. These waves come in many forms, each with a different wavelength and energy level. This variety gives rise to the electromagnetic spectrum, which we'll explore later. Some familiar examples include radio waves used for communication and broadcasting, microwaves used in ovens and for communication, infrared radiation felt as heat, visible light, the colors we see, ultraviolet radiation responsible for sunburns, X-rays used in medical imaging, and gamma rays, the most energetic type of radiation. For centuries, scientists debated the true nature of light. Is it a stream of tiny particles or a wave? The answer, as we now know, is both. But for now, let's focus on the wave-like behavior of light. Imagine the calm surface of a lake. Now picture a gentle breeze creating ripples that travel across the water. These ripples are similar to light waves propagating through the fabric of space. Just like water waves, light waves have crests, high points, and troughs, low points. They carry energy as they travel at the speed of light, which is approximately 299,792,458 meters per second in a vacuum. To truly understand the language of light waves, we need to learn its alphabet, the key characteristics that define them. These are wavelength, frequency, amplitude, and speed. Wavelength. Imagine measuring the distance between two consecutive wave crests. That's the wavelength, often represented by the Greek letter lambda. It's a fundamental property that helps us distinguish different types of waves. It determines the color of visible light and the energy level of the wave. Shorter wavelengths mean higher energy. For instance, ultraviolet light has a shorter wavelength and higher energy compared to visible light. Frequency. Now picture yourself standing at a fixed point as waves pass by. Frequency is the number of wave crests that pass by you every second. It's measured in hertz, and is inversely proportional to wavelength. Higher frequency means higher energy. Radio waves, for example, have lower frequencies compared to X-rays, which have much higher frequencies and energy levels. Amplitude. Think of the height of a wave from its resting point to its crest. That's the amplitude, which determines the intensity or brightness of the wave. Higher amplitude means a brighter light or a louder sound. This is why a high-amplitude sound wave is perceived as louder. Speed. All electromagnetic waves travel at the same speed in a vacuum, the speed of light, which is approximately 299,792 kilometers per second. However, their speed can change when they pass through different mediums, like air or water. This change in speed is what causes the bending of light, known as refraction. For example, when light enters water from air, it slows down and bends, creating phenomena like rainbows. Understanding these characteristics is crucial to unraveling the marvels of light and other electromagnetic waves. They are the building blocks that allow us to explore and comprehend the vast universe of electromagnetic radiation. Here's where things get really interesting. The nature of light has puzzled scientists for centuries. Light doesn't always behave like a wave. In fact, it can exhibit properties that are quite different. Sometimes it acts like a stream of tiny energy packets called photons. These photons are the fundamental particles of light. This mind-boggling concept is called wave-particle duality. It's a cornerstone of quantum mechanics. It means that light can exhibit both wave-like and particle-like behavior depending on how we observe it. This duality is not just theoretical. It's been proven through various experiments. Think of it like a coin. A coin has two sides, heads and tails. You can see either heads or tails, but never both at the same time. Similarly, light can show wave or particle characteristics, but not both simultaneously. Similarly, light can behave as a wave or a particle, but not both simultaneously. This duality is context-dependent. The photoelectric effect is a prime example of light's particle nature. This phenomenon was explained by Albert Einstein. When light shines on a metal surface, it can knock electrons loose, creating an electric current. This is a direct demonstration of light acting as particles. This phenomenon can only be explained if light is considered a stream of photons, each carrying a specific amount of energy. The energy of these photons is quantized. On the other hand, the diffraction of light through narrow slits demonstrates its wave nature. This is a classic experiment in physics. When light passes through a narrow opening, it spreads out, creating interference patterns that are characteristic of waves. These patterns are a hallmark of wave behavior. Section 6. When waves collide, interference and diffraction. Imagine dropping two pebbles into a still pond. The moment they touch the water, ripples start to form and spread outwards. The ripples created by each pebble will eventually collide, creating intricate patterns on the water's surface. These patterns are not random, but follow specific rules. This phenomenon is called interference, and it's a fundamental property of all waves, including light. Interference can be observed in various scenarios, from water waves to sound waves and even light waves. When two waves meet, they can either reinforce or cancel each other out, depending on their relative phases. This interaction is crucial in understanding wave behavior. If the crests of two waves align, they create a larger wave, constructive interference. This results in a wave with greater amplitude. Conversely, if a crest meets a trough, they cancel each other out, destructive interference. This can lead to a reduction or complete cancellation of the wave. Diffraction is another fascinating wave phenomenon that often goes hand in hand with interference. It's the bending or spreading of waves as they pass through an opening or around an obstacle. This bending is more pronounced when the size of the opening is comparable to the wavelength of the wave. Think of ocean waves bending around a pier, or sound waves reaching your ears even when you're standing behind a wall. This is diffraction in action. These phenomena, observed in both light and other types of waves, provide further evidence of the wave nature of light. They help us understand the dual nature of light, behaving both as a particle and a wave. Section 7. The electromagnetic spectrum, a rainbow of possibilities. Now that we understand the basics of electromagnetic waves, let's explore the full range of their diversity. The electromagnetic spectrum, it's a continuous range of electromagnetic radiation organized by wavelength and frequency. At one end of the spectrum, we have radio waves with the longest wavelengths and lowest frequencies. They carry information for radios, televisions, and cell phones. As we move along the spectrum, wavelengths decrease and frequencies increase. We encounter microwaves used in ovens and radar systems, infrared radiation, which we feel as heat, visible light, the only part of the spectrum our eyes can see, ultraviolet radiation responsible for sunburns, X-rays used in medical imaging, and finally, gamma rays, the most energetic form of radiation used in cancer treatment and astronomy. Each part of the electromagnetic spectrum has unique properties and applications, making it a valuable tool in various fields, including medicine, communication, astronomy, and more. Section 8. Exploring the unknown, the future of electromagnetic radiation. Our journey into the world of electromagnetic radiation is far from over. Scientists are constantly making new discoveries and finding innovative applications for this versatile form of energy. From developing faster and more efficient communication technologies to exploring the universe with powerful telescopes that detect different parts of the electromagnetic spectrum, the possibilities are endless. Imagine a future where we can harness the power of light to create new energy sources, develop faster computers, and even cure diseases. The future of electromagnetic radiation is bright, and it's up to us to explore its full potential. Section 9 conclusion: the universe in a grain of light. We've journeyed through the fascinating world of electromagnetic radiation, uncovering its wave nature and exploring its diverse applications. From the colors that paint our world to the invisible signals that connect us, light is the language of the universe. Understanding the wave nature of light allows us to comprehend the world around us at a fundamental level. It opens our eyes to the beauty and complexity of the cosmos, revealing the interconnectedness of everything. So, the next time you gaze upon a starlit sky, listen to the radio, or marvel at the colors of a rainbow, remember the invisible waves that make it all possible. The universe is speaking to us through the language of light, and it's up to us to listen and learn. Keep exploring, keep questioning, and never stop being curious about the universe and its many wonders.